All right, welcome back. Next section, 9.2, we're talking about series, and then the nth term test for divergence. So one important application of infinite sequences is representing infinite summations. So if a sub n is an infinite sequence, then we have this little e, it's called sigma, but it stands for summation, and we're going to start at 1 to infinity, that's what those stand for. Okay, so we're n equals 1, we're going to start there all the way up to infinity, and we're always going to use those positive integers, right, like 1, 2, 3, 4, 5, and so on. A sub n equals, and then a sub 1 plus a sub 2 plus a sub 3 dot 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 plus a sub n plus, we got to keep going up there, right, like a sub n plus 1 and a sub n plus 2 or whatever. So that's called an infinite series, or just considered a series. Okay, so this is a series. The numbers a sub 1, a sub 2, a sub 3 are just the terms. Okay, just the terms. Unlike sequences, which always start at 1, sometimes we begin at 0. Okay, and then we just go 0, 1, 2, 3, and so on. An infinite series adds up to all of the terms of the sequence, while a partial sum adds only numbers up to a certain number. So, for instance, if I have s sub 1, that means I just want to find the first term, which is a sub 1. S sub 2, it means I take the first 2 terms and I add them up. S sub 3, I take the first 3 terms and I add them up. S sub n is the first n terms. So a million or infinity or whatever that value is, we can find that value out using some different rules. All right. Fantastic. Let's move on. So some definitions for divergent and convergent. For the infinite series, okay, this here, the nth partial sum is given by this. So we already know that from above. S sub n is equal to the partial, the values of a sub 1 through a sub n all added together. If the nth partial sum converges to s, then the series converges. The limit s is called the sum of the series. And therefore, if s sub n diverges, then the whole series diverges. We'll get to what that means. We'll do some examples as well. But I want to find and calculate the fourth partial sum for each sequence, or each series here, sorry. So I'm going to take the first 4 terms. So I'm going to say, okay, well this is 1 over 2, right? If n is 1, that's 1 over 2, plus 1 over 2 to the 2, which is 4, plus 1 over 2 to the 3, which is 8, plus 1 over 2 to the 4, which is 16. If I actually do all that math, I get the fourth term, the partial sum of s sub 4 is equal to, you add this up as a fraction, find common denominators, and you're going to get 15 over 16. Okay, that's what you get for that one. For this one, okay, well, because there's no variables here, no values n or whatever, it's just 1 for everything. So the first sum is 1, the second sum is 1, the third sum is 1, the fourth sum is 1, so that means s sub 4 is 4. Okay, 1 plus 1 plus 1 plus 1. And then the last one over here, because I have a negative 1, that means I'm going to have an alternating series, right? So if I plug in 3, I start with 3. That's negative 1 to the third, which is negative 1, divided by, what? Divided by 3, right? Divided by 3. Plus, now it's negative 1 to the fourth. Well, that's positive 1 over 4. Plus, now it's to the fifth, which is negative 1 over 5. Plus, now it's positive 1 over 6. And if I do that math, I'm going to end up with the sum of the fourth partial sum is equal to negative 7 over 60. Okay, and that would be your simplified answer there. Properties of some infinite series. These like seem pretty familiar with all of the limits in the sequences in the last section, but it's basically the same. So if a series is equal to a, so it adds up all to a, and then b sub n adds up to b. Okay, then we can say that c is just some number, right? C is just a constant, so some constant times that. I can take the c and I multiply it by the series, which is n equals 1 to infinity of a sub n. So we know this here is going to be a, and then c times a. So that's what we can do there. If we're adding the two series together, then I can add the two values, what they equal together. And if I subtract them, then I can definitely subtract them. You cannot necessarily multiply and divide them because that's going to be very different depending upon what your sequences and series, or what your series actually are. So it's only adding, not necessarily multiplying and dividing. They don't work all the time. They could in some cases, but not all the time. So we're going to talk about determining whether a series converges or diverges. There are several tests that you'll have to know. Like, you got to memorize all these. The first is what we call the nth term test, not terse, I don't know what that is, for divergence. So what this says is if the limit as n approaches infinity of the series a sub n is not equal to 0. So if it's equal to anything else, then the actual series, so this is the sequence here, the series is going to diverge. Okay? But the converse is not true. So that means if I took the limit and it equals 0, then the series could converge. So it might or might not converge. We don't know, but this is the only one that's actually true. So if the limit of the sequence is not equal to 0, then the series is going to diverge. All right, we got to know that. So here we go. First one up. I have the series from n to 0, or from 0 to infinity of 2 to the n. Well, the limit as n approaches infinity of 2 to the n is actually going to equal infinity, which is definitely not equal to 0. Okay? Therefore, using this test, we know that this is going to diverge because of the nth term test. Okay? Diverges because of the nth term test. That's what it says. This one here, number 2. We're going to take the limit as n approaches infinity of n factorial over 2n factorial plus 1. So, this is actually 2 times the n factorial, not 2n. So it's not 2n factorial, it's 2 times n factorial. Like this is in parentheses right here. Okay? Alright, cool. So what's going to happen? Well, the top, if we think about it, is going to grow as fast as the bottom. N factorial over n factorial, think about it, they're going to grow the same rate. So I take the coefficients, which is the horizontal asymptote test we talked about in the last section, and this is going to go to a half. And so this is not equal to 0. Therefore, this series is going to diverge because of the nth term test. It's not equal to 0. This one, if I took the limit as n approaches infinity of 1 over n, this is equal to 1 over infinity, which is equal to 0. And so because this is equal to 0, the test is inconclusive. Inconclusive. We do not know if this is, we know it's not going to necessarily diverge because it's not equal to 0. But it could, so it's inconclusive. So therefore the series might converge, or it might diverge. We don't know what's going to happen. Because this equals 0 from up here, we don't actually know what happens. It could converge, it could diverge, we don't know. The only thing we can tell is if the limit of that sequence is going to be a number not 0. So if infinity, obviously it's not 0. Half, obviously it's not 0. So that's the only thing that we can tell. We cannot tell if it actually equals 0. Like what happens? Like, I don't know. Alright? So that is it for this video. Hopefully this video is short, and I will catch you in the next one. Deuces.